Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. Quick reminder that if you do enjoy the show, please do consider supporting us through Buy Me a Coffee. It really helps us to keep making the show. Today, I'm joined by Vikramank Singh, who will be telling us everything we need to know about Panda, performance debugging for databases using LLM agents. Vikramank is on the AWS Redshift team, where he's a applied scientist. Welcome to the show, Vikramank.
Hey, thanks for having me. Good to be here.
Fantastic. The pleasure's all ours. So can you tell us a little bit more about yourself and how you became interested in database management research?
Sure. So, as you said, I'm currently working as an applied scientist here at Amazon. I'm part of this team called Redshift, which is a data warehousing service in AWS. And I joined AWS probably 3 years ago, and that's my introduction to databases. So I actually had no background in databases as such. So I did my undergrad in computer science, spent some time working at Facebook in computer vision, machine learning, as software engineer, moved to Berkeley to do my master's. And when I did my master's, my research was mainly around reinforcement learning or controlled or decision-making systems. And then I moved to AWS and I joined a team which was primarily working on databases. So all the problem statements that we used to solve were related to databases using machine learning. That's why I think we sort of picture or pose ourselves as people who work on ML for systems. So we use machine learning to solve problems in the systems domain. That's my introduction that's how I got introduced to problems in databases. I initially started working with this team called RDS, which is Relational Database Services in AWS, and started working on some very interesting problems for RDS customers for about 2 years. And then I moved to Redshift, and quickly that's where I am.
Awesome. Yeah, that's fantastic. So you finally found your way to databases, to the Holy Grail, right? Mm-hmm. So you finally made your way. Yeah. That's awesome stuff. So today we're going to be talking about LLMs, and I know they're all the rage at the moment. So can you maybe kind of start off for the listener, giving us some sort of background on kind of what LLMs are, and kind of we can talk a little bit about performance debugging as well, and why that's important and hard necessarily in databases.
Sure. Yeah. So again, I'm no expert in LLMs, and I will probably not dive too deep into what LLMs are and so on, but just to give a very high level stuff. The way I see it, LLMs are, I feel, are what we call generative models. When I say generative models, again, not to dive too deep into the technical stuff, but they learn the distribution of the data they train. And when we talk about the generation process, it's just sampling from the distribution and sampling in some meaningful way. And when I say a meaningful way, in this case, it's an autoregressive way, where what you generate at time t+1 probably depends on the past. It can be an independent generation as well, where whatever you generate at t+1 has no relation to what you generate at time t, but that's not autoregressive. So why we are interested in LLMs nowadays is because LLMs have been primarily used for languages, because they're language models, and language by default tend to be autoregressive or have a sequential behavior to them. So what you see at time t+1 is probably related to time t, which is related to time t-1, t-2, and so on. So I kind of look at them as autoregressive generative models. That's what LLMs are. And the reason they've been so fascinating is because of the use cases they've been applied with. So now, earlier you used to train these models like small corpus of data, but now that we have the right amount of resources in terms of compute and energy, we can train them on probably a large chunk of internet. And then they turns out they can do some pretty interesting stuff. So that's a very high level, very superficial way of explaining what LLMs are.
No, that's fantastic, because I have sort of, I've messed around with ChatGPT, and it's fantastic, and I find myself using it more and more every day, kind of for just various different tasks. I don't tell my mum, but for writing the message in her birthday card, I found it very useful for that. So I'm giving me inspiration anyway for me to fine tune, shall we say. But yeah, so that was a fantastic description of kind of what they are, and that was really, really insightful. So I guess kind of with that then, so we've kind of got these LLMs, and they're super useful. How can we then apply that to performance debugging in databases, and kind of tell us more about the performance debugging angle of your work?
Yeah, I mean, that's the question that I've been asked before as well. So, like, when you think of LLMs, databases are not the first thing that you think of a use case, right? So, why is there, what's the overlap between databases and more specifically debugging databases and LLM? So, let's talk about debugging databases first. And I was, again, as I said, before joining AWS, I had no clue about what data. I mean, I had clue about what databases are, but not a deeper understanding of how they work and how people actually use them in production systems. So when I started working at RDS, I saw a lot of customers how they use their databases. And when I say customers, these are people, let's say they are database engineers in their own respective teams, in their own companies. These are database DevOps people, a lot of development engineers who rely on the databases day to day. Maybe they maintain, let's say, tens or 15s of databases for their company. And how do they make sure that the database is performing at a level that they want? So there are various tools out there that these people try to use to monitor health of the database. Now, again, the term health of database is still not very well studied or defined. So let's say a health of database is something that you can think of like the rate at which your query executes on an average continues to remain the same, or P90 or P95, whatever. So there are different metrics that you can use to measure the health of database. It can be how many number it can be number of connections over time, it can be query latency over time, it can be number of active sessions over time. The different definitions of what is the health of database. So we can pick any one of them. And there are like tons of telemetry data. So this is a time series data. So at every time point you can measure the average latency of all your query. So on Monday, you can measure it, Tuesday, Wednesday, and so on. So this is the time series data. And usually in production, these database engineers, they monitor about tens to hundreds of these telemetry data. And this is usually what starts as a database debugging process. So when you want to understand how your database is doing, you look at this dashboard, which has like tons of telemetry data. You try, and for each metric, you have some sort of threshold over time that you have set. I would feel like, okay, if my average latency is beyond this, I don't care. Things are good. And if my average latency goes above this threshold, then something bad is going on. So that's where it starts usually. And the impact of this is gigantic. So like these dashboards that they monitor, that can have like any impact on the business. Because let's think about if that query is something, let's say you are some e-commerce company and some customer is trying to search for a product on your website and the page is taking too long to load. So the customer doesn't know what's going on in the front end, but on the back end, probably some query is taking too long to read your entire table or something like that is happening. So your query latency shot up, the page is not loading and the customer moves on to, let's say, a rival website. So it has like significant impact on companies' revenue and business model as well. So yeah, the database debugging is important. So these database engineers, they constantly monitor these telemetry data. And whenever they think something wrong is going on, some of their thresholds have been crossed, then they look into why something is wrong. So they look into each telemetry data, try to understand why things are going wrong. And for that, they usually go about reading a lot of documentations. So now when we talk about documentations, that's where the natural language comes into the picture. So there are like a bunch of open source documentations. There are a bunch of really good handcrafted documentations created by AWS, if it's an AWS database. And that's usually where they start with. They start reading why on this specific database engine, if a query is running slower, what could be the possible reasons? What are some actions that they can take? How can they fix it? Is there a parameter that they need to tune? Is there a query they need to tune? And things like that. So it's a combination of looking at this telemetry data and reading the relevant troubleshooting documents is what I generally call as a debugging process. And the problem with this process is A, the telemetry is long enough. So there are like hundreds of telemetry data that you need to monitor, which is difficult for a human being. And B, the documentation is vast. So it's not just one document per metric. There will be like hundreds of documents. And finding the right document, identifying the right solution from the document is not trivial. So the combination of this is very complex. And on top of it, this needs to be done in real time and on a continuous basis. So they need to monitor day in, day out, constantly keep doing this over and over again. So the way I see LLMs helping them is to understand this large corpus of natural language data, which is the troubleshooting documents, and then try to help them identify the right answers. And we'll talk later about how you can combine telemetry data and troubleshooting documents together using LLMs. But this is one place where I feel LLMs can be brought into the picture and help speed up the debugging process for databases.
Awesome stuff. So yeah, just to recap there, we've kind of got on one side, we've got this whole like thousands of metrics that we like in terms of telemetry data that was kind of hard for us to sort of kind of have it all in our head at one time. And then you've got these massive amounts of sort of documentation. And then all of a sudden you've got a customer screaming at you because their query is not fast enough and they're going to lose a sale to a rival company.
Exactly.
Okay, yeah, I can understand the motivation here now very clearly as why this DevOps engineer would kind of want someone else to help them sort of kind of solve this problem quickly. So I guess that's a nice sort of segue into Panda. And yeah, so give us the high level elevator pitch for Panda then. How is this going to make my life better as a DevOps sort of DBA, someone running one of these managed database systems?
Sure. Interesting. So let me think of like what's the elevator pitch for Panda. So as I explained in the column, right, that's exactly what Panda is designed to solve. So when we thought of Panda, the goal of Panda is to answer this very specific question. And the question that we try to answer is, what are some of the essential building blocks that we need in order to safely deploy any black box large language model for debugging databases in production? And the goal of the recommendation of the production, the goal of output of this Panda is to make sure it generates accurate, verifiable, actionable, and useful recommendations. So sure, you can put anything inside a language model, you can generate some stuff that does make sense, but is it useful? Is it verifiable? Is it accurate? These are the questions that we want to answer with Panda. And that's like why we want to build Panda and what exactly Panda is. Panda is a service or is a framework that combines the power of telemetry and documentation using language models. That's what Panda is. So it combines information. It's able to extract information from telemetry data. It's able to extract information from documentation, and then it's able to combine those two pieces of information together to generate. That's what Panda is.
So yeah, before we go any further, why Panda?
Yeah. So this, yeah. So the naming, I'm sure I didn't spend too much time thinking about the name. And when I wrote this long sentence, so I didn't have an acronym for it. So I just wrote what this thing does. And what it does was it was performance debugging for databases using language models or large language model agents. And when I started looking at this large sentence, I was thinking of one word description. I just picked random stuff from the sentence and made this word called Panda. And I felt like Panda is a word that usually people are aware of in the computer science domain because of this Panda library in Python. So it came out naturally to me. So I just picked that name.
Yeah, nice. I like that.
Nothing deep in there.
Yeah, no, and I like that also as well because like I guess when I thought like Panda, they're kind of cuddly, they're like, and it's like something that's going to help you. And I'm struggling to debug this problem. I need to go and cuddle my Panda, and he's going to help me. I don't know, thinking of something like that as well. Anyway, awesome, cool.
Yeah, it's an interesting.
Yeah, that's kind of what I was thinking about it. But anyway, cool. So you listed the 4 properties there of kind of what you want this LLM sort of debugging database agent to have. So kind of taking those sort of design goals and the kind of the sort of the thing you wanted to build, how did you go about sort of like what's the architecture of Panda? How did you sort of go about realizing this sort of goal?
Sure. Yeah. The way we started thinking about this solution was okay. We had one thing clear that we know from our domain experts. We know usually what database engineers think about or what the process looks like when let's say a database engineer starts debugging a problem. So we tried to write that process down. That's what our starting point was. So what did they do? So okay, we looked at they look at a bunch of telemetry data. That seems important. Once they start looking at telemetry data, they have some sort of knowledge about what each metric means and how different metrics connect together. So that piece of information is relevant. Second, third, what do they do after that? So let's say they identified there's 5 out of 100 metrics that do seem anomalous. What do they do after that? So then we realize what they do is for each of those metrics, they look at their documentations. So they have some predefined set of rich documentation and they start looking at them. So that's the third thing we found. So our model needs to do that. then when they start going through each of those documentations, they try to find things like what are some usual cases where these metrics become anomalous. So what are some usual problems? What are some usual root causes for this problem? Once they identify that, they try to find what are some fixes for these solutions, which are usually in the same documentations. And once they find those fixes, then they try to think which of these are feasible given the time span that I have, given the condition that my database is in right now. Is it feasible for me to, let's say, restart the database and tune a parameter, like change the value of parameter? Or maybe it's not possible for me because of the production database. I can't switch the database off and restart it again. Okay, so next solution, things like that. And then they finally apply this fix on the database. So there are like multiple steps that we follow the database engineer of how they try to fix a problem and then replicate that exactly with a language model. So that was the design of thinking phase of how the system should eventually look like. To sum it up at a very high level, so there are 4 key design components. First is what we call grounding. So we needed a module in Panda, which we call as grounding component or grounding module. Now, what this grounding module does is we know that telemetry is very important. So if you can pick any language model like GPT or Llama or any language model and ask it a question about database in natural language, and it will generate a bunch of recommendations. So it's not that we're training a language model from scratch. That's not the goal. But the goal is to ground the language model more by giving it the right context of the database. So how do we do that? And what we found is that the database engineers, they use telemetry to do that. So how do we connect? And language models are not trained on telemetry data. They're not trained on these large metrics. So how do you combine the telemetry data with language models such that the language models can now understand the context of what the database is experiencing right now to generate answer? That's what we call grounding. So we needed one component called grounding. The second component we called was verification. So we believe the system should be able to verify the generated answers using some relevant sources and produce citations along with it. So the end user can eventually verify what the output is, where the output is coming. Now, this is easier for humans because when database engineers, they try to fix a problem, they read these documentations and they know exactly the source of these documentations. So they know exactly, when they don't know the person who wrote it, but they don't know the organization where the document is coming from. So there is some sort of trust behind the truthfulness of the documentation. So we want to build that into the system. Third is what we call affordance. So what we believe is that if the recommendation that the Panda provided is actionable, the system should be able to estimate and inform the user about the consequence of the action. Now, this is also very important. So if, let's say, this Panda says, increase your number of CPUs from 16 to 32, what's the consequence of that action? The consequence could be increase in cost. The consequence could be your query latency could go down. So we want the user to know what will happen, what's the counterfactual, or what will happen if they do this, if they do that, before applying that recommendation. And fourth, and the last component is feedback. So we believe the system should be able to accept feedback from the user and improve over time. So if Panda is running on a database, there's a database engineer that says, okay, you said this last time, I applied the recommendation, didn't fix my issue. So we want the system to take that into account the next time it generates an answer. So these are like the 4 key principles: grounding, verification, affordance, and feedback that kind of build the Panda.
Awesome. Yeah. So grounding, verification, affordance, feedback, kind of just running through them one by one then in maybe a little bit more depth. So on the grounding thing, because when you were speaking earlier on, you was kind of talking about these LLMs are great for sort of kind of large corpuses of natural language. But then we kind of want to combine this with these metrics. And I was thinking even the time series, like, hang on a minute here. How do you kind of resolve this fact that these things expect one type of data and then you've got this massive amounts of different type of data that's really important? So how did you go about sort of bringing those two things together in the grounding?
Exactly.
That's
exactly. And that I think is one of the most interesting contributions of Panda. And there's some so this area is again very active in terms of research. you'll find like new interesting papers and ideas coming up every other day, where people are trying to experiment with numbers, experiment with math and LLMs. So this, I forgot the name of the exact paper, but there's some recent paper that came from, if I'm not wrong, Google or Stanford somewhere. I forgot the name, but they showed that you can actually uh, input the raw telemetry data in the prompt, and it will generate statistical answers about the metrics. So if I give it, let's say, a month long numbers of data, which timestamps and some value, and ask, let's say, what was my average query latency on Monday? It's actually able to infer what Monday means from the data, extract the numbers, and sum it up and give you the answers. So there's some very there's some very interesting emergent behaviors coming from LLMs, and which proves that these are not just random word generators. They're learning something much more interesting and fundamental underneath them. And that's a whole different conversation people are having, where are these language models actually learning a model of the world? Are they learning something more sophisticated underneath them that we don't know yet? But we feel like they're just generating next word, but they're not just generating next word. How are they generating the next word is very important. That's a whole different story. But yeah, so coming back to this telemetry. So yeah, there's some very interesting work on how you can combine telemetry with text, with language models. And what we did in our case, let me talk about that, is what we did is we took all the telemetry data. So, okay, so you have a database. Data for that database, when a customer asks a question, what we can do is we have simple tools that can go and extract the telemetry data from the database. So we don't need LLMs to do that. So in the paper, we have a very complex architecture of the entire framework, and there's one small component inside what we call grounding mechanism. Inside that grounding mechanism, there is one small component called feature extractors. So those feature extractors, what they do is, there are no LLM involved yet. What they do is, for a given database, they connect the database itself and extract all the relevant telemetry metrics. When I say relevant, I mean all of them. They extract all the telemetry metrics. So for example, there could be database parameters, there could be configuration knobs, SQL statistics, all the active sessions, all the database counters and everything for the last 7 days. So they extract all this telemetry data. Now, again, before involving language models, what we do is we run these statistical algorithms on top of the metrics. So what we want is, we went back to the human. So we looked at how humans look at these numbers, look at these telemetry data. These humans, although they don't look at everything, they look at metrics that behave anomalously, or they look at metrics which behave differently than usual. So identifying what a metric, when a metric is anomalous, is not something we want LLM to do. It can be done very well with simple statistical algorithms like outlier detections or change point detections or segmentation algorithms and so on. So we did exactly that. So once we extract these telemetry data, we ran some statistical algorithms to identify what are the metrics that are anomalous, that are different than the usual behavior, and how are they different? Are they spike up? Are they spike down? Are they level shift? What are they? Point anomalies, segment anomalies, and so on. So we extract all these features using statistical algorithms, and then we have a separate module that converts these features into one-line summary, and that's where LLMs come into picture. So we give the metric name, we give the definition of this metric, and we give the type of anomaly the metric has, and ask the LLM to generate a one-line summary of this. So we'll say something like the metric called pick some metric, number of rows. So a metric called number of rows for the SQL query has a spike in its last 7 days, with a value of, let's say, 120, whereas on average the value seen for this metric on this database is 50. So there's like one sentence summary. And we repeat this for all the metrics, and this gives us like a small prompt of what the anomalous metrics are, how are they anomalous, and why are they anomalous. And we put these prompt together, and then we combine it with the rest of the prompt that we generate. That's how we convert the telemetry of that.
So yeah, that makes total sense. There's a kind of a conversion where you go ahead and you kind of give it to the LLM in a format that it can handle. Awesome stuff. Yeah. Cool. So yeah, I guess kind of then the next step with the verification, when he was talking about that, kind of this idea of the provenance of where the information's come from, and kind of, because there's this sort of I mean, I can go on ChatGPT and it can give me some garbage citations for something, right? And it can and it looks really like realistic and it looks great. It looks like if I go on Google Scholar, the paper doesn't exist. So yeah, how did you how did you counteract that sort of thing then? Because I guess it would be LLMs would be subject to the same sort of thing, the ones you used. So yeah, how did you tackle that?
Exactly. That's exactly the problem with LLMs, right? So if you ask LLM itself to generate a citation for the answer, the recommendation that it made, it will definitely give you a right citation. But most of the time, the citation would be just a hypothetical citation or something that's garbage. And in fact, there's a recent study, we can link that paper in the description, but there's a recent study that showed that only 50%, or 51.5% of LLMs generated answers truly support their citations. This completely undermines the trustworthiness of the real world. So, and this is where these things like become questionable of being useful in production or in the real world. I mean, they all sound very interesting and fascinating for research or for demos, but then we can't reliably use them on a continuous basis in real world if things like these happen. So this was like a challenging component to us as well. Now, what's the extreme end? So like the best possible thing you can do is have a human verify everything. That's like the golden truth. And it's possible, but it's like highly unscalable and very costly, right? So you can't have a human verify every single generated answers because it's both tiring, it's not cost effective, and you can't have as many humans that are experts in databases to verify everything. So how do we do that? So we did something that was in between. Inside the verification mechanism, we have two things, two components, two subcomponents. One component is what we call answer verification, and one is what we call source attribution. So for answer verification, we use natural language model itself. So what we do is we frame this problem as something, again, in literature, it's called natural language inference, NLI, as a natural language inference task, where we reuse the pre-trained LLM to act as a verifier and produce a label as accept, reject, or neutral, given a hypothesis. And when I say hypothesis is the generated answer. So what we do is we give the generated answer to the LLM, and then we also give a premise. Now, premise is all the relevant troubleshooting documents. So what we do is we basically ask LLM, if this is the answer and this is the context, what do you think? Does the answer come from this context or not? And give me an answer in terms of yes, no, or maybe, or accept, reject, or neutral. So what we expect the LLM to do is to look at the context and try to see if there's an interesting overlap between the answer and the context. Now, this can be done without LLM as well. You can just do some very simple textual mapping where you can see how many words are common between the answer and the context. But the problem with that is that the answer that we are given to the LLM is actually generated by the LLM. So, and LLMs are known to paraphrase or rephrase. So simple textual mapping might not be the very best solution because that would always give you very small amount of overlap between the generated answer and the context, because the answer could be rephrased, could be paraphrased, and so on. So the goal of this natural language inference problem is to make the LLM look at the context, look at the generated answer, and tell us if the generated answer is coming from the context or not. And again, sure, this process is not optimal. I mean, it's not the best process because, again, in some sense, you're asking the student to correct their own answer paper, right? So you're saying, okay, you wrote the answer. Now, here is the true answer, correct it. And you can cheat, right? So that there is possibility of cheating, which we're aware of. And one way of mitigating it is to make it do multiple times. So we try to randomize it. So instead of asking it only once, we ask it 3 times and try to then take an average of what the response is. So it may cheat once, it may cheat twice, but we're expecting it to not cheat n number of times. And that n is high parameter that we can tune. You can increase that number of repetitions as many times as possible. So yeah, this process is not perfect, but it's something that kind of works in reality as of now. And once this answer is verified in some sense, where LLM feels that it is indeed representing, the generated answer is representing the true context, then we move to source attribution. And source attribution is something simpler, because source attribution is now we want to cite the lines that are there in generated answer. And again, we kind of follow the same process. So source attribution can again be done in two steps, two ways. One is you can go line by line in generated answer and give that line to LM and ask which exact paragraph in the context is this line taken from. And it can give the exact paragraph, and you can cite the paragraph number or page number from the documentation. That's one way. And second is exact text overlapping. So if you see the exact verbatim sentence taken from the doc, you can just pick the doc number, page number, and cite it there. So use a combination of both, and that will give you the source attribution, and then we move forward. So yeah, these are the two components in verification.
Awesome stuff. Yeah, that whole kind of thing about it kind of not cheating every time is interesting. And I mean, we'll probably talk about the best end to choose when we talk about the implementation and in your evaluation potentially. But I mean, is there not a worry that sort of the more you do it, it gets better at cheating and it cheats more the more you run it? Is that sort of a concern, or is each kind of run sort of independent of the previous run?
Yeah, so we make sure that we don't run this in the same context, or in the sense that we don't want to run the, like, each time we ask the same question, it's not in the same chat or in the same sequence.
So we wipe its memory essentially every time and say, do it again. Okay, so it doesn't think, I cheated last time, I'm going to cheat again.
Yeah.
Right. Okay. Cool.
And you can even play with the the subtle things there. So you can even play with the there are different parameters in the language model that you can tune. So for example, you can vary the quotient of innovation in the model, or the quotient of the rate, the temperature of what I'm blanking out on that word, but it's, I think, when you want the model to be stricter or be more creative. And you can tune these models to not be very creative, where they try to generate something that's, so if you, in more technical terms, you want the model to generate samples that are very highly likely from the distribution and not out of distribution. So if the model is more creative, it can generate things that it is slightly less trained on. But if the model is less creative, it will generate something that is exactly what it is trained on. So when we do answer verification, we want the model to be extremely less creative. So you don't want them to think or wander in the areas where they're not trained to wander in. And that would prevent them from being so cheating is if you think of it, cheating is a creative mechanism. They're trying to be very creative there, and that's why they're cheating. So you want to control the level of creativity in these models, and if we can control that, we can somehow push them to not cheat.
It's funny about cheating being a very creative endeavor. I mean, you hear these stories, don't you, of people kind of going to extreme lengths to get exam answers and stuff like that. I think you may as well just revise for it, because you put enough, like, you've put more work into be a good cheat, right? So yeah, but anyway, cool. So yeah, affordance. Let's talk about affordance. So how do you go about kind of taking this and turning it into, this is what the consequences would be if you did this in practice? Because obviously the how do you put a cost on it in terms of like the financial impact or the performance impact? Yeah, this is like a big space. It's often quite hard to know what the consequences of an action will be. So yeah, how did you go about sort of breaking that down and estimating the impact of something?
Yeah, correct. And this, I would say, is like the most controversial, most the most raw component in the system is this mechanism, because I would say we've not even thought of this component really well. We are still at a very early stage. We're still thinking what this affordance mechanism could encompass. So, like, for example, we don't even know what an affordance means here, right? Like, for example, if the model generates something like tune the add an index on this table, if that's a recommendation, how would you go about estimating the impact of adding an index to, let's say, something on query latency? It's very difficult for, like, forget about LLM doing this. It's very difficult to even build a statistical model, a database model to do that. Like, what's the impact on P50 or P90 of your query latency if you add an index on this table? It's very difficult to build that statistical database model. So it's not clear at all how can an LLM do this. So for now, what we have in a affordance mechanism is it's extremely heavily guarded with a bunch of guardrails. So what we do, we start off with something in the answer generation. So when the model generates an answer, we force it to be actionable, to generate an answer that is actionable. So now what does actionable mean? An actionable mean we wanted to generate something with respect to a parameter that can be tuned. We want so it can't say something like tune your number of CPUs. That's not actionable. I mean, sure, it is actionable in the sense that you can tune it, but what to exactly? So we wanted to generate things like, since we are telling the system that my current number of CPUs is 16, I don't want to tell me increase the CPU. I want you to tell me increase to what? So increase from 16 to 32, or increase from 16 to 64. So those are the kind of answers where we force the model to generate. So we always force the model to generate something very specific that can then be converted into a statistical equation, mathematical formula, and we can estimate the impact. So now when I say impact estimation, we always want to drive the impact estimate towards a specific metric. And right now there are a bunch of metrics that we care about. We care about the average query latency, and we care about the average number of active sessions in the system at any point in time. So we want to estimate the impact of these actions in terms of these two metrics.
Now, I was just saying, interesting. Like, how did you settle on those two metrics?
Yeah.
Like, what was the decision there of how to actually pick those two out? Because there's a lot of things, right?
Correct. Yeah. So again, the choice is, I would say, still a design choice here. We designed the system based on how we've seen the RDS engineers or the customers think about their system. And usually what we have seen is people care about the metrics like what's the average query latency, and people usually care about what are the sessions that are active and what are they waiting for. So how many sessions are waiting and what are they exactly waiting for? So that metric seems to be pretty simple but pretty impactful when people monitor data performance. So we picked these two metrics, but yeah, these can be any metrics. Now, the impact estimation model is a simple statistical model. So think of it as a function which takes as input the parameters and output the value of your query latency. So these are like simple statistical models that were trained on the feed data. Now, there are two ways you can train this model. These models can be customer specific or they can be feed level model. When I say customer specific, what I mean is that and when I say model, you can think of it as a simple neural network model. It can be a regression model, any sort of model, a random forest decision tree, whatever. So this regression model is trained on, when I say customer specific, it's trained only on this customer's data on which we're running Panda. So if Panda is being run on your database, it's only trained on your database. And the goal for that is to make sure that the regression model is trained on the metrics that's coming out of just your database. So how is your query latency changing with respect to CPUs? You just want to model that. That is customer specific models. We can also have fleet level models where we can, instead of estimating how query latency changes with respect to CPU on your database, we estimate it across the fleet, across all the customers. So that model will give you an average estimate. So like on an average, how does query latency is impacted if you increase CPU? Or on an average, how is query latency impacted if you decrease CPU or if you things like that. So that's what we call fleet level models and customer specific models. And we have simple models on both these fronts that we try to plug into Panda and estimate the impact. But again, these are very, very early stage right now where you don't have impactful models there yet. So we are still trying to play around with simple regression models and trying to estimate impact.
Nice. Yeah, it's obviously still sort of an early sort of project, right? In terms of its life, its lifespan.
Exactly.
But yeah, it's not going to be the finished, polished article yet. So no, that's cool. So yeah, I guess there's one more component then, and this is the idea of feedback and getting the model to improve over time. So how does that kind of component look in the current iteration of Panda?
Sure. So in fact, this is the very first mechanism that the models, the input sees. So like when you query Panda with the question is first sent to the feedback mechanism. And the goal of that is think of feedback mechanism as a simple database that stores questions, answers, and feedback over time. So whenever a final answer is sent back to the customer is asked to give a feedback in form of +1 or -1, like thumbs up or thumbs down. And that feedback is again sent and saved in this database. So if let's say you've been using Panda for over a week now, and let's say you have seen around 100 questions, every one of those questions is stored in this database. And this database is, think of it as simple as like 3 columns, and row and column database, and you have 3 columns. First column is your question, second column is the answer that Panda generated, and third column is feedback, which is thumbs up and thumbs down. Now, if you ask a new question to Panda, Panda will take that question and go back to this database and look for, was this exact question or a similar question being asked before. And if it does find a match in the database, then it will look at when was that question asked, because the temporal aspect is important. Like if I ask something like 1 month ago, it's probably not relevant anymore. So we keep that window to 1 day. So if we find an exact match or a similar match between your new question and an existing question in that 1 day window, we'll probably retrieve the answer and send it back to the customer without going through the entire generation process, which might be a high latency process. So that's like one use case of feedback mechanism, where we can generate answers faster, and they can be repetitive, they can be similar to what you've been asked before in the same 1 day window. And if it is, we'll surface the same answer. And then we'll tell customer that this is an answer from the question that you asked in the past. If this is not relevant, you can re-ask the question and mention that in the prompt, that you gave me an answer, I didn't like it, and generate a new one for me. And that would bypass the feedback mechanism altogether.
Fascinating. So it's kind of like a mini Stack Overflow, essentially, kind of in the whole thing as well. So cool. Yeah. So we've covered off all the components there. And there's a lot of moving parts to this system. So can you tell us about the implementation briefly, maybe, and like how do all these things fit together? What does the actual code look like? And what's the user interface like as well? Actually, like, is it simple? Is it just a bad enter texting? Yeah. So tell us a little bit more about the implementation.
Mm-hmm. Sure. Yeah. So again, the way we coded Panda up was not was a very experimental coding, in the sense that it started off as a very small project, a very experimental project. So the code base that we have is not very like a gigantic code base. Everything is like well thought of and written in a way that's like all fail safe. It's still very experimental, very raw, very early stage right now. So that's that. But the interface of the user is kept to be very simple. So interface is as simple as a chat interface. So everything is done in the backend. So once you trigger Panda, it connects to your database. So again, in order to connect to the database, you need to give it the credentials of your database. That's a separate story. But once Panda is up and running, the interface is as simple as a chat interface. There's a question, there's a bot, and there's your answer bot. So you keep asking questions, their answer will be generated. They'll be having, every answer will have its own citations. And if the answer has an impact estimation, we'll have it, otherwise it won't. Because not every answer's impact can be estimated. So the impact estimation won't be there for every answer. If we could find a relevant impact, we'll add it in the answer, otherwise it won't be there. The interface is very simple, it's very simple like a chatbot.
Yes, interface we're all kind of familiar with. Yeah. Cool. So let's talk some results then. So you've evaluated so we can talk about that as well, how you went actually about approaching sort of evaluating it, and then let's talk some results as well. So let's start off with like how you went about evaluating it first, then we can talk about the results.
Sure. So I think we discussed this at some point in our chat today, where the golden rule for the highest level we can uphold Panda is with the human evaluation, right? So again, just the one thing we need to clarify first: what exactly are we evaluating? Are we saying what's the standard we are holding Panda up to? Are we saying Panda is something that can generate answers better than human? No. What are we saying is that Panda can generate answers better than an existing language model. So that's the bar we want to test Panda on. So, and the reason we want to clarify that is because we don't want to compare the Panda answers to a human answer. We can't compare Panda to an existing database engineer and say, okay, this guy can beat this guy. No. What we want to do is we want to compare Panda with an existing language model, which in this case was GPT-4. And we want to say that since Panda has all these 4 components, affordance, feedback, grounding, and verification, with all these 4 components, Panda can perform better as compared to language. So that's the goal. So how we started running, set up the experiment is, since we don't have any ground truth label for any recommendation, we do use humans to evaluate the answer. So what we do is we pick 3 different humans with 3 different level of database knowledge: a beginner, an intermediate, and advanced. And we show them, we generate, we picked 50 prompts, 25 from a Postgres engine, 25 from a MySQL engine. And all these prompts were engineered in a way that we have been seeing more commonly in how customers ask questions about their databases. So customers' questions are usually not very detailed. They're always very, in some sense, it's correct because they don't have, not all users have a good understanding of what's going on in the database. So they usually ask questions which could be very generic, very high level, and they expect the system to infer all the relevant stuff on its own and generate an answer. So we intentionally kept the questions to be very high level and very short to see how LLM responds to those questions. So we gave this 50 prompts, 25 Postgres, 24 MySQL, and then we generated the answer using Panda and using GPT-4. And we showed these 2 answers to these 3 evaluators and asked them to rank or score the 2 responses on 3 aspects. And those 3 aspects were, first was trust, second was understanding, and third was usefulness. So trust, as in, if you read these 2 answers, which one do you generally tend to trust more? And second is, if you read these 2 answers, which one do you understand better? And third was, if you read these 2 answers, which one do you feel is more useful to you? And they're asked like your thumbs up and thumbs down on each of these 3 aspects. We average their scores, and then that's the response table that we generate in this paper across these 50 evaluations.
Awesome stuff. So yeah, I guess, yeah. What's the big reveal? Tell us how did Panda do?
Panda was found to be often. So again, let's go dimension by dimension. So on the dimension of trust, experts found Panda to be at more than 90% of time a better candidate than GPT. And the reason for that was, I think, is citation, which we also mentioned in the paper, that with every response, Panda generates citations, which is usually an indication of trust, where customer can now go, or the user can now go and look at a citation, go to that very link, very documentation, and read exactly in detail if they have any questions around the recommendation. So that kind of generates more trust. So for more than 90% of times, Panda was rated higher on the trust. The interesting thing was understanding. So when we asked the scorers to to score based on understanding which of the answer they understood more, the beginner scorer was around 40-60%. So they rated Panda 60%, but GPT 40%. So there's not that big of a gap. And the reason for that was GPT answers, if you look for it, they're highly verbose. It will probably generate like 100, 300, 400 word passage for you. And for expert or intermediate people who know exactly what they're looking for, this kind of highly verbose answer is waste of time for them. They want something very specific, very actionable. But when you look at it from a beginner's lens, reading the entire paragraph does make sense for them, because now they kind of understand the problem much more better and they can ask follow-up questions. So that's where we found that beginner people were in some cases liking the responses from GPT better, because Panda was being a bit too specific. In the sense, okay, they said that tune parameter X. Now, what if they don't know what parameter X is? Or what if they don't, they've never heard of parameter X. So they need some more context, some high level stuff, and then probably narrowing down to the parameter, which GPT was able. So GPT-4 never gave the parameter name or the value, but gave a very good verbose explanation of what are the possible problems that customer could face with respect to this details, and they found it to be more understandable.
Sorry, just real quick. Do you think that could be something you could incorporate as part of the model? Kind of the person asking the question could definitely be like, "Hey, I'm a beginner, I'm an expert, blah blah blah," and that sort of like would definitely influence the verbosity of the output. But yeah,
exactly. And that's exactly what we thought of after the experiment. So we wanted to incorporate that in the system, where when you instantiate Panda on your database, we also want to assign a role for the user who is using Panda. So you want to assign the role in the sense like, who are you and what do you expect from Panda? And Panda would take that into account when generating answers. If your role is a beginner, it will be very verbose and very, it will have a lot of introductory stuff before coming down to the actual actionable details. So yeah, that was very useful in the experiment as well. And I think the third dimension was usefulness. On usefulness, again, we found the intermediate and advanced folks to have at least more than 90% of approval rate for Panda, because they found it to be more actionable, very specific with the exact parameter names, exact parameter values, and so on. Whereas GPT was, again, very highly verbose or very high level, very generic. So yeah, the useful dimension was similar to trust dimension, but the interesting one was understanding, which had something for us to learn from.
Yeah, for sure. I mean, it feels like it's a clear indication here of sort of the usefulness and kind of the efficacy of Panda kind of going forward. So I guess where do you go next, and what's the next on the research end? Obviously, there's things to make it production grade and a lot of polishing, maybe to get everything kind of stitched together and working well. But yeah, what are your next steps?
So I think it's Panda is very far away from production. I would say it's still very still taking baby steps. It's still in the place where we are still trying to falsify hypotheses around language models. So it's still very experimental right now, I would say. And there are a lot of interesting areas that we can exploit or we can take Panda into. So, for example, the first thing that we found in our analysis was Panda is so sure you can chat with Panda, but debugging, the process of debugging is very incremental. So like debugging is never one shot, it's multi-shot, right? And the right answer of why a problem has occurred, the root cause could be multiple. There's not always only one root cause for a problem. So sure, Panda generates something that may be right, but it's not the only right answer. What if something else happened? So let's say you're seeing an increase in your query latency, and Panda said, okay, you have an increase in query latency. It's because you didn't have an index on this column in this table. Sure, the customer didn't have an index on that column in the table, but is that the real root cause? Or what if they just increase in workload at that time? Or what if it's something related to locking? So there could be more than one answer to a question. And we want Panda to be more human-like in that sense. So instead of like jumping to conclusions, we want Panda to be iterative and think in all different directions. So in some sense, we want the Panda to generate a hypothesis tree where each branch is one root cause, and then go on and validate each branch, and then generate a recommendation, which is not just one single recommendation, just forcing you to take something or believe it, but it should give you more like an analysis of all things possible and let the customer pick which one they feel is right.
Yeah, that's fascinating because in practice these problems there can be layers upon layers. And has there been sort of did you encounter where you solve one like but inadvertently cause another problem by solving that one problem, if that makes sense? Like, I don't know, you like so you add an index and then that caused something else to blow up. Like how would you handle that?
Yeah, exactly. That's exactly the problem that Panda would fail on, right? So it's the answer that Panda generates is very confident, but it has no clue what that could trigger later on. So sure, we have the affordance mechanism, we have the place where you can estimate the impact of this. That's the goal. The goal of that component is exactly to solve this. If you recommend something, we want the customer to know what is the impact. Is it going to trigger something else, or is it going to increase something else that we don't care about? So things like that. So yeah, Panda is at that point, Panda is not equipped to solve these kind of problems where down the line things could break because of the recommendation that we make today, and we want to fix that before even thinking of productionizing it.
Before unleashing it in the wild.
yeah.
Cool, awesome. Yeah, so I mean, still though, I mean, this feels like it can have a kind of really big impact kind of going forward. So yeah, I guess kind of could we elaborate on that a little bit? Like, what impact do you think Panda could have in the future?
Mm-hmm. Yeah, sure. The place where I feel Panda would impact the most is reducing the amount of time database engineers or DevOps folks spend on debugging databases. So, like for example, from the scenario that we have seen in databases or in real world nowadays customers, we feel like we've seen that customers spend about 10, 15, 20 minutes, even like several hours debugging one single problem. And the goal is like, if let's say a customer on an average spends like 45 minutes debugging the problem, can Panda bring it down to, let's say, 5 minutes or 10 minutes? And saving that 15, 20 minutes or half an hour worth of effort on one single problem is a significant amount, because this multiplies really fast. So if a customer spend, let's say, debugging hundreds of problems a week, you could spend like multiple hours worth of their effort on these problems. And the interesting part there is, we don't want Panda. Again, the Panda's goal is not to replace the database engineer. It's to assist them. And that distinction is very important, because once you make that distinction, the bar at which you qualify Panda to be useful significantly lowers. So what I mean is, we don't want Panda to be absolutely accurate or 100% perfect all the time. You want it to be perfect most of the time, because eventually the final action that is supposed to be made is to be made by the human. We want Panda to be accurate most of the time, so that it can help the human narrow down the space and find the right fix immediately. So if we were to say that Panda is to replace the database engine, then the quality or the bar that you will hold Panda to is extremely high, and you might never reach that in a few years or whatever. And that would kind of make the whole point of research more, because then there's certain things that you can never fix, or at least not fix in the near future, and these kind of work will never be useful or never be made available to public. But I think the fact that we are thinking of it more as an assistant rather than a replacement, that lowers the bar and allows for more creative and aggressive things to be done in this space.
Yeah, it allows it to become practical, right? It allows us to kind of keep the human in the loop, allows it to augment the human, make the human more efficient. And then obviously, once you're using it in practice, well, then you start insights about how it can, you learn things about it that maybe you wouldn't have thought of, rather than waiting for this sort of utopia future where we have this perfect sort of human equivalent, right? So yeah, no, I definitely agree with you on that one. Cool. Yes, I mean, I how long have you been working on this project? You said it's pretty early days, still in the sort of
it's
the whole
very,
project.
it's super early. I started working on this probably a year ago.
Okay, cool. So kind of about a year. Cool. So yeah, kind of across that year, what's the sort of the most interesting thing you've kind of learned while kind of working on Panda? What's been the biggest surprise?
Mm-hmm. I think the biggest surprise was how much improvement you can make so again, before going there, I think one thing that we missed out in our conversation is, what is the actual LLM Panda is using? Because Panda itself is using a LLM, right?
Yeah.
And we never talked about what is that LLM. And I've mentioned this in the paper, but we use GPT 3.5, which is an inferior model to GPT-4. So the goal is to show that so the Panda is not a new language model, right? So the goal of Panda is not to come up with yet another highly complicated billion parameter language model. The goal of Panda is that if you pick any language model and plug Panda to it, can it improve from the vanilla model? Even if I pick, let's say, Claude V2, or if I pick a Llama model and plug Panda into it, can Panda plus Llama beat Llama? That's the goal. And that's what we're striving for. And that was very eye-opening to me, because I felt, when I started this research, I felt like GPT-4 or GPT 3.5 was already like surpassing almost everything, every expectation. But when we started the answers seemed correct, factually correct, but they're not very useful. And that was eye-opening to me, because every time I asked something related to databases, it was able to give me as a 1,000-word answer, but all of it made sense, but none of it was useful. So it was kind of like a aha moment where we realized that, okay, this is something that can be exploited, because people were going all bonkers with this, like LLMs coming around, and they're like, okay, they're super useful, like, highly productive, and so on. But we felt like we dive deeper into it. There's this vast amount of improvements that can be made. And when we started working on it, just by adding telemetry information, just by adding simple statistical models around it, the kind of improvement in the responses that were made was very, very interesting to us. That's something we didn't expect this to take it that further. So I think that was something that was interesting.
Yeah, that's fascinating. It kind of makes you kind of wonder how many other sort of applications there can be that takes a similar approach, right? Of taking kind of an LLM, taking GPT, and then kind of putting this sort of wrapper around it and kind of building on top of it. Yeah, I'm sure we're going to see loads of really fascinating sort of products and applications built on top of it over the coming years for sure. That's cool.
And
by the way, really
it's already started.
yeah, continue.
So yeah, just to piggyback on a thought, there's already a bunch of research on using LLMs as tool management. So instead of us making LLMs do everything, make the LLM act as a manager, where it doesn't give you an answer, but it decides what is the right tool to pick to give you the answer. So in this case, think of it like when we convert telemetry to text, LLM is not converting the telemetry to text, but LLM is deciding what is the right algorithm to convert telemetry. So do I run anomaly detection? Do I run outlier detection? Do I run change point detection? What is the right algorithm? Because what you care about would be different. Let's say I only care about decreases or declines in the metrics. I don't care about an increase. So that information is irrelevant. And if somehow LLM can figure that out, it can query the right tool. So there's a bunch of interesting papers. There's one interesting paper I read recently, which was called Tool Formal, where language models can teach themselves to use tools. And that's also like very interesting area of research going on, where using LLMs as tools manager or using LLMs as reasoners, which can create the right tool, is very interesting. Because if you think of it, LLMs are trained on this vast amount of knowledge base, which makes them very good which make them generate good answers on an average, because they're trained on large amount of data. They're not trained on specific stuff. So they're not experts, but they're good on an average. And people who are good on an average, who are trained on like these vast amount of data, are good leaders, or not leader in the sense like good managers, right? Like if you think of it, like LLM has seen a lot of things, which makes it a good manager. So instead of asking it to solve every single fine detail in the problem, you can ask it, since you've seen so much, tell me who is the right person to fix it. And that is what LLM is better at, instead of asking it what is the right answer. So ask it who is the right person to solve it. And that LLM will give you a better answer there.
Wow. All the managers and sort of exec level people in the world better start worrying then if it can become a kind of effective manager, right? So yeah, but that's true. But like kind of that point of being sort of, if you can be sort of average or above average and kind of across a broad spectrum of things, they tend to be sort of good managers, kind of good leaders. And yeah, so no, that's a really interesting point. Cool. Yeah. So tell me about your creative process then, Vikramank. How do you go about kind of thinking about ideas, generating ideas, and then selecting which ones to work on for a prolonged period of time? Yeah, so let me inside your brain.
Yeah, it's an interesting one. I think what has worked for me, I'm sure that the different strategies people use to test their creative self and to come up with these interesting ideas. I think the one that has worked for me is to try out things and fail fast instead of like thinking of the best idea. So like the whole idea of Panda came up instantly when I started testing. Like when I started trying ChatGPT, my guess was that it would probably give a much better answer than what it gives, because it's trained on so much of data, right? So it should be better than that. But when it gave some answers, the first thing that I thought of was like, why is it not able to give this answer? And it's probably because it hasn't seen telemetry data. That's what's missing. So then I quickly built a demo of what if I'm able to supply telemetry data in some language form? Can we improve it? So I felt like an iterative demoing process kind of helped me a lot. So if I would have sat down and trying to design like the entire architecture 1 year ago, I wouldn't have reached anywhere, because I couldn't see a lot of problems that I saw after demoing stuff. So I feel like iterative, fast failing approach kind of helped me complete this architecture at least.
So in terms of the demo, and this was a case of, okay, was it demoing to sort of the team and sort of like, oh, here's this, and then you kind of thought afterwards, this didn't work actually, or got some feedback and thought, oh, that could have been different, and that's the way you approach it. That's fascinating. That's I've not had that answer before. That's really cool. Everyone answers this question differently. It's brilliant to see how we're all so different. But yeah, no, that's fascinating. Cool. I think I might try that. See how it goes for me. Awesome stuff.
Of not knowing what I don't know what I don't know, right? Or what is that the right phrase? Yeah, exactly. And it's very difficult to sit at T0 and predict T infinity. So the faster you move towards T infinity, as you'll find new ways of exploring. It's like these 4 components that we talk about in Panda, right? It's not that we started thinking of it that way. It just, when we built the entire framework, component by component, based on the feedback that we got, eventually we realized, okay, this is what one framework is. This is what the other framework is. It's all like working backwards instead of working forward.
Yeah. Awesome stuff. Cool. Yeah. Anyway, so it's time for the last word now. So, what's the one listener what's the one takeaway you want the listener to get from this podcast today?
I would say, I think the last point that we discussed is probably an interesting one. I feel people can take away from this because, again, if you look at the work, I'm neither an expert in databases nor an expert in language models. And we still came up with something interesting in this combined space because of just quickly experimenting and failing on these crazy ideas. So I think that's one takeaway people can take. So you don't have to be an expert in either of the domains to come up with something useful, because what's useful and what's interesting are very two different things, because something that can be absolutely uninteresting could be very useful, and something that is super interesting can be extremely useless. So I would say if you want to build something, aim for useful, and eventually you'll realize that what you end up building, it will become interesting at some point, because interesting kind of is a state that evolves over time. If you have a useful problem, start building it. Don't care about how complex this model is going to be or how sophisticated I can train this model to. Start with something very simple and try to solve a use case, and that, like Panda does, and eventually it will become interesting because no problems. Because I'm sure you can never think of all the problems at the very start. You'll always encounter problems that will make things more interesting.
I think that's a brilliant line to finish it on. So yeah, thank you so much, Vikramank. It's been an absolute pleasure to talk to you today. And if the listener wants to know more about Vikramank's work, we'll put links to everything in the show notes. And yeah, thanks again, Vikramank. It was a fantastic episode, and we'll see you all next time for some more awesome computer science research.